Hi, everyone, and welcome to a new year of our NACE Calgary webinar program. I'm your host, Brett Johnson, Program Chair for NACE Calgary. So today I get the honor of welcoming my own Pembina colleague and friend to our series, Nicki Robertson. Nicki obtained her undergraduate degree in composite materials engineering from Wyona State University, followed by earning a doctorate in materials engineering from the University of Alberta. She has worked in the pipeline industry since 2007, both through academic research and as a pipeline operator. Her work experience has been mainly in pipeline integrity. However, she's also been involved on the pipeline construction side. As such, she has authored 2 midstream operators pressure testing standards. So Nicki, thank you so much for joining me today. It's an absolute pleasure to have you on our channel here.
Thanks so much for having me. This is one of my most favorite topics to talk about, and look forward to creating some foundational knowledge for the industry, both from the design and construction side all the way through to the pipeline integrity side. It's a unique topic like that. So.
No, that's perfect. So today you're going to give kind of a whole nice introduction on pressure testing and what that's all about.
Yeah, you bet. And I even have a special guest speaker who's going to join us, Louise Azucenza, and I'll introduce him later in the talk. But for all the real tough nitty-gritty questions, we'll put it on him.
No, that's fantastic. Well, I'm really looking forward to that. But before we jump into that, none of what NACE Calgary can do would be possible without our annual sponsors. Their contributions allow us to be able to provide this webinar series to our membership at no charge. So today I'd like to highlight one of our gold sponsors, PipeTech. So it's extremely important that a pipeline be in clean condition prior to an inline inspection run. Loose or adhered deposits and scale can cause a range of issues, from sensor liftoff that causes tool sensors to be ineffective to a pipeline becoming plugged with deposits in front of the inspection tool. These issues can require costly repeat runs of the inspection tool, or in the worst case, the tool can become stuck in the pipeline and need to be cut out to remove it. Pre-inspection line cleaning should be treated as a project and done with new pigs for the express purpose of cleaning the line to a suitable level of clean for the inspection tool. PipeTech has been involved in multiple high-risk projects around the world, ranging from fluid management to progressive cleaning of solids disposition. They regularly work with end users to establish and maintain pigging programs for maintenance, as well as project work, including line prep prior to ILI, line prep for chemical application, and progressive cleaning, just to name a few. And of course, to all our other annual sponsors are a huge reason why we can do what we do. Our sponsors help fund several initiatives that NACE Calgary takes on to promote the knowledge of corrosion, sustainability, and asset integrity to our industry and the next generation of engineers. To each one of our sponsors, we thank you for your continued support. So if you haven't had the chance yet to check out our YouTube channel, please go ahead to our website at nacecalgary.ca, and there you can find the direct link to our channel that has all our past presentations. And if you enjoy presentations like this one and you're looking to get away to beautiful Edmonton for more, be sure to check out the NACE Northern Area Western Conference, scheduled to be run on April 11th to the 14th at the Edmonton Convention Center. So registration is now live at nawc2022.com. So Nicki is going to be giving her presentation live. Be sure to stick around after the presentation, and we'll then move into a live Q&A session. Please submit your questions in your Zoom client by clicking the Q&A button on the screen. If you are joining us from YouTube Live, please enter your questions in the comments there, and I'll be sure to ask them as well. So without further ado, Nicki, go ahead, take it away and share your screen.
Awesome. Thanks, Brett. It's my first Zoom call, so it's pretty awesome. So today I'll be just going through the basics of pressure testing. I call it 101. So it's going to give folks the opportunity to be able to ask tougher questions and improve your individual testing program. So typically I like to start with why. However, since this is a 101 webinar, I'm going to start with what is a pressure test, and we'll work our way counterclockwise through the diagram to answer the key questions surrounding different phases of the pressure test and who's involved in what. And as I already touched on earlier, a lot of these topics today are much more complex than I'm going to make them out to be. And so this is really just that base foundational level of knowledge. And as I mentioned, Louise is here today to help us answer any nitty-gritty technical questions as part of this work. And as always, I love case studies, so let's just jump right in. So is every pressure test the same? No, it's not. We need to have a project-specific test plan that answers all these questions. And I'll show you what that is in just a few slides. So here is our agenda for today, is to start with what, work our way counterclockwise to when, and we'll go through the details regarding different documentations and parts like that as well. And I'll share some cool case studies. So what is pressure testing? It is pressurizing the pipeline to a significantly greater pressure than the pipeline will ever see. A pipeline is sectioned into manageable test sections, which are capped by the end by a test head, as shown here, that are designed specifically for the job, or in the case for smaller pipeline jobs, say 8-inch and below, they can be blinded off at the riser with a flange, and the flange can act as the test head. Water or methanol mix is typically used as the fluid used in pressure testing, sometimes otherwise referred to in the industry as hydro testing, although we're applying pressure inside the pipe, so I like to go with the word pressure test. You might be wondering, why is water used? Well, it's because it is a non-compressible liquid fluid that in the event of a failure, there's less stored energy. In addition, H2O is used because it has a high specific heat capacity, meaning it takes more energy to change the temperature 1 degree Celsius. And this is a really important point, as we'll touch on it later with regards to pressure monitoring. On the right here, you will see a schematic from a survey that captures the elevation of the pipeline. This is typically taken from the survey company and provided as part of a thing called the test plan that we'll discuss in a bit further. This elevation profile defines critical high-low points throughout the pipeline to enable designers to design the target test pressures that will be experienced during the test. So you might ask, what is a pressure test? As per CSA, it is defined both as the strength and leak test component that occur above the maximum operating pressure. How much above the MOP is based on the pipeline design, the class location, the product service type, the elevation profile, and a lot of and as well as this guidance is shown in CSA table 8.1. Highly recommend. If you don't have that, put it in an easy to find location. However, there are many more activities associated with pressure testing before and after the test. And let's go through these activities, because these are all included in the notorious test plan. This is my favorite component because the test plan really sets you up for success for all of your activities surrounding a pressure test. So let's walk through them one by one. When you fill the pipeline, it comes from a fluid source, and this is very dependent on how large your job is. So for big mainline jobs, you take it from rivers, lakes. For medium jobs, it can be dugouts. And for smaller pipelines, it can be trucked in from either a municipal water source or a nearby water source to fill your pipeline. And there's lots, I don't want to simplify this again, but there's lots of work associated with planning the logistics to obtain sufficient test medium fluid used in the test, as well as environmental and regulatory permits in order to obtain that water. So, however, we're going to focus on the technical today. So once you get the line filled, there's this very important period called stabilization that is required in order for the fluid to equilibrate, which means come to the same temperature as the ground temperature. Now, it's important that you achieve this equalization period so that you don't get any potential pressure fluctuations that are not actually indicative of what you're trying to test, which is the pipe. So, and this is one common shortfall that I've seen in many projects of not actually having sufficient time to stabilize the test medium. And this can really lead to unwanted, really long leak tests that can cause some issues with logistics. So highly recommend, make sure you have some instrumentation on so that you can define when you've achieved your stabilization period. And then once you're ready to what we call is squeeze. And this is when you pressure up the pipeline to the target test pressure as set by the designers. And this is dependent again on your class location, your product type. And in the event relative to the maximum operating pressure, this can sometimes be greater than 150% of the maximum operating pressure can be seen at points throughout the line. And to put it in further in perspective, these pressures are sometimes greater than what's experienced in the steel mill, and even that greater than the specified minimum yield strength, or what we refer to as SMICE, of the pipeline. CSA allows, depending on material, of course, allows up to 110% of the specified minimum yield strength to be reached. And we'll go into what you need to do in those cases next. So you get to your target test pressure, and this is where you call in the phase called strength test. And this period really proves that the pipe can contain the pressure that it's rated for. Next, you move into the leak test. Depends spec to spec, but I recommend a slight decrease in pressure to get to the leak test. And what this really means is it's a containment of volume still at minimum pressure greater than the MOP. So once the pressure and temperature are constant, what you'll get is this locked in phase. And that's when you know you have a successful test on the leak test. Then you go to depressurization, needs to happen at a controlled rate, dewater, and then we need to dry and batch the pipeline to deal with potential issues with internal corrosion and etc. So here's an overview of what's included in the test plan. There are multiple phases, and all of these phases require planning, logistics, and communication. So you might think, well, Nicki, there's lots of things going on. What's the most important thing? If you've learned one thing from my presentation today, or you recall from your previous education, it is the fundamental principle that pressure, temperature, and volume are all correlated. I pause because pressure, temperature, and volume are all correlated. So when we go back to thinking about our different test stages, when we're doing our squeeze, we're adding volume into the pipe to increase pressure. And so when we go up to greater than 100% of specified minimum yield strength, you're required by CSA to do something called a pressure volume plot, okay? And a pressure volume plot monitors the correlation between how when volume increases, pressure also linearly should increase. And so we measure it relative to a 0.2% offset, which is the elastic limit of steel, to ensure that we're not plastically deforming the pipe as we're pressurizing it up past its minimum yield strength, okay? And our volume and leak test component, our volume in the pipe remains constant, and we monitor pressure and temperature because this is a long-term hold, typically anywhere from strength test can either be 1 hour or 4 hours, and a leak test is always 4 hours in CSA pipelines. So these are the key topics to have in your mind. So can you pull up the poll for why should we pressure test? I want to hear it from you. We'll give you guys a few ideas. I should have probably put an answer in there because the regulator says I have to. That's typically a good one. That's why we do lots of things in life. All right, Brett, let's just close the poll and I'll take a screenshot of the answers. All right, so can everybody see hopefully on my screen? So we have 60% of people are correct. It does provide evidence of pressure containment. You are correct. It provides evidence of caution against failure. Justification to operate against MOP. This is an incorrect answer. It gives you justification to operate to the MOP. Trick question there. And it also eliminates imperfections. That's right. My favorite point is that this really is providing evidence. Evidence that you can really truly use and lean on that, yes, this pipeline is going to be safe to operate. And that evidence becomes a life of asset record that the folks in integrity, such as myself, use to go back to understand what could be the largest imperfection in the pipe at the time that it was constructed. So it has a lot of value, this pressure test. Also, yep, and it establishes our safe maximum operating pressure. And in my opinion, this is the most important part of the pipeline construction. And it is also sometimes the highest risk activity because it is done at the end of the job. And people get tired, but it's still a very critical activity that we need to have our wits about us. So why test? As you mentioned, this is the final check of the asset. It is the ultimate QC activity, and a successful test provides certainty that the line is fit to operate. So here are a few examples of when we found that maybe this one isn't fit to operate. So here's an above ground HDD pre-test that was unable to contain pressure that happened in Alberta within the last 10 years. And it opened up because there's an existing flaw in the long seam within the material. So here's the water escaping the pipe. Pretty easy, hey, to see that water's leaving. And on the right here, you can see an X-ray, and this darker region is the long seam, and the black portion is actually the through wall long seam failure. So it's pretty important to, before you pull an HDD, to have that 1 hour strength test confirmation that you don't have a defective pipe before you spend all that money pulling it through your drag section. Next here is a below ground mainline test, which was unable to hold constant pressure. And this slow drop off in pressure was actually also caused by a long seam imperfection. And this was observed in the leak test because it's below ground. It's tougher to identify and those issues, which is why we have that minimum 4 hour leak test. And here is again another X-ray where you can see the lack of fusion that's shown and demonstrated here by the yellow arrow. Other cases are kind of more obvious of test failures. And here's an image of a pressure test chart records where it's recording pressure over time. So this is one of these old analog wheels where we have the red line here is temperature and the green line here is pressure. And we're monitoring it on a spin chart, right? And so as it's being pressurized up, you can see that it's not really a straight line going to pressurization. It's kind of curved. So the field finally decided to stop pressurization. And you can see that it immediately was experiencing a drop in pressure. And so realistically, there's lots of signs that as you're getting that curved approach, that there's an issue and that the pipe is either deforming or unable to contain pressure. So this is another example of why it is so important to have experienced and competent people that are at site overseeing the testing of your pipeline. So that takes me to also why test. So just to give you some more shameless self-promotion, I wrote a paper in 2018 that kind of goes through the framework of some lesson learned, so feel free to reference that. But it's good that we understand our foundation. We have laws and acts and regulations that we must follow as prudent operators. Then there's codes and standards that really help us define and streamline what that is in order to meet those acts, laws, and regulations. And then lastly, there's company standards and specifications. And these are critical to define at your organization how you're going to do your testing activities. Get that final check of the asset. So in a company standard, would be my recommendation of where to put this, rules should be clearly defined. I've highlighted 4 key rules that occur in pressure testing. And let's start with the designated engineer. They're to take professional responsibility for the test, both establishing the test pressures that need to be met during the test, giving their expertise to ensure you get an appropriate test, and then lastly, actually validating those results. And so a little tidbit of knowledge that I'll just give to everybody is a PEGA in December of 2021, last month, issued a draft for review, which is the field practice guides of engineering and geoscience work. And in here, they're following a similar approach, if not the same approach, as what's already implemented in BC. And that's actually mandating that there is an engineer who takes responsibility for the final acceptance of the full design and construction. And so a role and responsibility in your test spec that highlights this is recommended. The project manager is always accountable for absolutely everything and making sure that all the key stakeholders are plugged in at the right time and that they're following the adherence to both the code and regulation, but also the company specifications. The contractor plays a massive role in pressure testing. They're the ones who create the plan. They ensure that all the equipment, materials, labor is there on site to actually get a successful test, that everything that's on site's in good working condition, and that they have sufficient manpower to ensure that if there becomes a problem where you need to hold it longer, or if there is a possible failure, that they're ready to respond to that event. And then the other key person is a company representative or a quality individual, an inspector, who can also lend their expertise to ensuring that the test is being followed as per the test plan, and that we're getting the right documentation to prove all the hard work that's gone into it, that it actually did happen. So there are many different roles that happen, and at different stages in the test, they flip from responsible, accountable, consulted, and informed. So to just give a brief overview of what that looks like, Louise and I, as part of Pembina's pressure testing specification, came up with kind of a visual RACI chart to show at what stages are which roles engaged during the pressure test. So both from the planning perspective, from the execution perspective, if stuff goes wrong and you're into a test failure and you need to restart that execution and start all the way again from the beginning, and then the cleanup and sign off of documentation. And so I would recommend that this be done for each company to fit in with the activities that you do. And so where do tests happen? They predominantly happen in the field, below ground, with small amount of areas exposed at the ends, which is shown here on the big picture of a big test head on a big mainline job in the summer. Above ground tests are also done for pre-grills as that quick quality check, as I showed what can go wrong if you don't do that. And then also sometimes in this shop test for pre-tested pipe for smaller quantities, for cutout sections. And this is what is done for integrity work as well. And so you note here, see the bottom left, this is a picture of hoarding where you heat and the exposed ends in the winter to make sure you don't get freezing of both your instrumentation lines, and then you don't get an ice plug as well. So how do you heat it? Well, this is connected to a heater here that is on site. Boilers are also used in cold weather to heat the water to prevent freezing. Water trucks can transport small volumes of water to site. The fill pump is also used to fill the pipeline, and this can be used from the natural water source through the side or used during when you're squeezing it to stabilization. So then the pressure truck is it either have a fill pump or a higher rate fill pump, which here we're showing as a pressure truck to squeeze the test section. And then finally, you need an air compressor on site to be able to dewater and dry the section. So what about instrumentation to get a good test? We need a dead weight. I don't have a poll on this, but does anyone know what a dead weight is? Is it your typical ball and chain? No, it is not. It actually refers to the apparatus used to ensure accuracy at reading the pressure gauge digitally, known to be the traceable, recordable correlation in pressure. And so here's a schematic of what mechanical dead weight looks like, where you actually have a physical weight that correlates to the pressure as it's connected to the test section. So this is the old school way of doing it, and I think the right way of doing it, is having one of these mechanical dead weights on every single test to make sure that all your instrumentation is working properly. This also avoids non-compliance in Alberta under Manual 5 to make sure that you're documenting your setup and you're verifying your instruments. And here is a test picture from last time Louise and I were both out on site together that illustrates what this mechanical dead weight looks like, connected into our digital dead weight over to our pressure charts. So you're familiar with this. This is our digital dead weight that should be part of our setup. And then we have these chart recorders. Chart recorders are analog spinners that spin as a function of time. You can set them on 1 hour, 12-hour, or 24-hour spin cycles. And you can have them be single pen or dual pen to take in pressure and temperature, or just pressure. And so we have everything connected in through the pressure recorder, through the assembly on one side, which is typically a test shack. And here's just a little schematic. Now, you don't have to record both. But, you don't have to record what's on the pressure recorder itself, because it's already a record in itself. It's a chart. The pen is doing the recording for you. But what you do need to add in is your manual dead weight measurements and your digital dead weight measurements into some type of test log. I like preferably to have a test log on paper. However, the AER does allow for digital records. Hey, what about temperature, Nikki? You always says temperature is important. Anybody who knows me knows my opinion about the word ambient. Ambient temperature means what is around you. And since we're testing the pipe, it's what's around the pipe. So in a buried below ground test, what's around the pipe is actually the soil. So you have the pipe temperature, you have the soil temperature, and you have the air temperature. These are the 3 temperature types that should be measured so that you can understand how the test medium fluid can be changing so that you can accurately monitor pressure, because again, pressure, volume, temperature are all related. And a digital probe is required for the key temperatures so that you can validate results that are on your chart recorder. So where do you put all these things? How do you set them up? So it's important that you have your temperature for your pipe and your soil to be representative of the majority of the test section being tested, which is to say that if it's mainly below ground, you need to have a temperature representation that is in effect below ground, not out here exposed to the elements. So here you can see that the temperature and pressure is backfilled. And this is from the Pipeline Rule of Handbook, about 20 feet. The failure to measure this ambient temperature of the test medium of the pipe is also a non-compliance. So next we're going to go to a poll. Now that I've taught you about temperature, my favorite topic, which probe is acceptable for a below ground test, mainline test? Is it A, on the left, temperature probe under a rag on a pipe, it's insulated, or is it B, pipe probe under buried soil? Okay, Brett, let's close the poll. See what you guys said. Oh, only 4. You guys are a smart group here. So only 3% of participants said that the pipe on the rag is acceptable. Pipe under the rag would be acceptable if we had an above ground test in winter conditions by where we were pulling an HDD section. However, we have a below ground test, and so therefore our probes need to be below ground. So, Nikki, you're talking about verifying instruments. When do you do this? You need to verify, not calibrate, but verify. There's a difference. Calibration means that it comes to you in a state that should be in working order, and you have a record to prove it. But you need to verify those instruments before the test, during the test, and after the test. And you do that by cross-checking different pieces of equipment to each other and monitoring if there's any differences or deviations between the two, and do they stay the same or do they skew during the test. Instruments can fail, and if the instruments fail and there is no redundancy, then you're going to be required to do a retest. So that's why, even though you only need one chart recorder of your record and one digital dead weight of your test log, it's always best to have a few chart recorders and a few locations where you have that digital dead weight so that you can see what your pressure is. So that way you can prove that you verified your instruments and nothing has failed on you. Here's an example of what can happen when instruments don't work. So this was an above ground pre-test that was being done, and it was being filled by a pressure truck, and the gauge on the pressure truck that was being displayed to the operators malfunctioned. And so what this led to was an overpressurization of the pipe on the right of way. And so another key thing that we need to help people in the industry understand is that energy is stored in the pipe during a pressure test, and you actually can experience it or see it with your naked eye until it is released. And so instrumentation in the right place is crucial to having a successful test. So we got a successful test, not like that last picture that I showed. What do we do after the test? You're talking about dewatering, drying, like what's all this about? So what this is about is you need to have an approach at your company. So on the right-hand side here, we have just kind of a quick flow diagram to say, okay, what water source are you using, or what medium are you using? And based on that, how are we going to protect the pipe from any deleterious effects from that test medium? And that's actually mandated in CSA under section 8.1.8. And we need to consider it. And so this is how Pembina has chosen to consider it. This may not work for your company, but something to take into consideration. And that is, you need to dewater, remove the water from your system. You need to make sure that, and for Pembina, we've decided to go with a methanol water wash, not sitting stable there, but just a quick wash to help speed up the drying process to get that accumulated water in those low-lying spots dissolved into that water methanol batch and to remove it from the pipeline. In the cases of native water, it is mandated to use a biocide application. So that way we don't have, and I got a whole bunch of corrosion engineers on the phone, we don't have a bunch of mick chewing away at our steel. And then the next kind of big consideration is what type of pipeline service is this going into? If this is a spec ethane line or spec natural gas line, it may not make sense to run a corrosion inhibitor because that's going to impact your instrumentation and your product delivery for your customers. And so you need to make a decision, which way are you going to go? Are you going to use a corrosion inhibitor, or are you going to go hardcore pure gas drying? There's a great paper back in 2018 called How Dry is Dry from Nova Gas, and they really explained how you can do dew point drying. It takes many hours. However, you get a great product in the end and is really your only option for those high purity pipelines. However, you have a chance to go with a corrosion inhibitor. Then you have to ask yourself, when are you going to put the pipeline in service? A lot of these big mainline jobs, you construct the line, but the day that you're done pressure testing in the ground and drying, the next day you don't throw the line into service. Sometimes there's sections done years ahead of time. And so that's when it's important that we put a nitrogen purge onto the line to kind of reduce the corrosion rate and preserve the great asset that the design, that the engineering teams have constructed. And so, yeah, that sounds great, Nikki. I don't really want to do that. That probably costs money, takes time. And that's true, it does. However, I just want to, this is some data stripped of the actual corrosion vendor, the chemical inhibitor company, that just kind of shows the difference in using a corrosion inhibitor. And so if you just leave it straight with air, you're going to get all the corrosion that you could possibly have in your line. You could keep your mick, you could have top of line corrosion, you could have bottom line corrosion. You could really end up with quite a mess. Now, if you purge it with nitrogen, you can reduce that quite substantially, almost a factor of five down to about 22% of the same corrosion rate. However, if you're to use an inhibitor, you can really drive that corrosion rate down, even if you're not using nitrogen. So just because the pipeline isn't going into service right away doesn't mean that we shouldn't be applying corrosion inhibitor after the hydro test to really remove any impacts of having that hydro test water setting up corrosion cells in your pipeline. And so I highly recommend that the folks in projects communicate with their integrity specialists to ensure that they're appropriately addressing the corrosion that could happen in their line, and integrity specialists working with your chemical vendors to find the right solution for your pipelines and your service. And failure to do this, there was another update to Manual 5 almost a year and a bit ago now, October 2020, that correlates a non-compliance with not following section 8.1.8 in CSA. Documentation. We're close. We're almost at the end, everybody. Quality documentation is required. If you don't take great documentation, then you practically didn't do all the activities that you said you did. So in our specification, and I would recommend company specifications or for even contractors, laying out the expectation of what records are going to be provided at what time throughout the project and what that final turnover package looks like, so that everyone's on the same page for what we need to do in the field to be able to have it accepted by the designated engineer and potentially your quality control individual or an MOP validator in your pipe, because this is a life of pipe record. Now, with all that said, let's do questions. And I'm just going to quickly introduce Louise, if you can come back onto the video. And Louise is a piping and pipeline engineer with over 15 plus years of experience in the oil and gas industry. He's been involved in a number of pipeline projects across BC, Alberta, and Saskatchewan. I've personally had the pleasure of working with Louise for many years, executing pressure tests, and also most recently the development of our pressure testing specification. And so I brought him in today because he has both that witnessed firsthand field knowledge, as well as he's worked at an EPC and creating test plans for multiple clients in multiple industries. So thanks, Louise, for joining us. I'm sure we're gonna have, I see that there's lots of questions and comments coming in. So I look forward to having you help me address them.
Sure. Thanks, Nicki, and thanks, Brett, for the opportunity today.
Thanks, Nicki. That was a fantastic presentation. Really appreciated, the information you provided. Lots of good case studies and a lot of good examples on there. So, a big kudos to our massive audience. This is an absolute record of attendees that we have on here. So it's fantastic. There's a lot of questions to get to. I know there's been a lot of questions that's been put in through the chat. I'll try to get through that, but we also have this wonderful little Q&A button on the bottom of your screen here that kind of helps facilitate a little bit easier and makes it easier to read and easier for me to kind of pick out all the nice chats on here. So let's start with kind of the first one. So, Nicki, where have you seen pressure tests go wrong?
So, good question, Brett. So where have pressure tests gone wrong? I think that we can categorize these into two different buckets. One is not following the plan, and then two is actually energy isolation. So when we go through not following the plan, I'm referring to a test plan that includes all phases of the test as well as contingency plans. So in the past, I've seen deviations from the test plan, uses of incorrect test medium, instruments that don't meet company specification. It says it in the plan, but then they bring it out to site and it's not actually what they said they were going to bring out, and not having the correct people on site. So you need to have that expertise. And then secondly, energy isolation. This is much more of a safety concern than it is getting a adequate test out of it, which is, I had an instance once in my career where on that test head, they didn't actually radiograph that weld because, well, it wasn't going to stay in the test section. So why bother inspecting it? Well, people are on site. Beside that, we need to make sure that there's a checklist before you just start squeezing up the test, that you make sure that everything has been inspected properly. And with that, just when you squeeze a test section, you need to make sure that you don't get any fluid coming back to what your squeeze source is. So in some cases you put check valves, and check valves are great, but that's not actually energy isolation. You need a double block and bleed valve so that you can actually isolate your pressure source from whatever you're testing. And that sometimes one or more pieces is actually missing from the site. And in some small cases, you know, you get some weeps or leaks from instrumentation. And that means we need to depressure to a safe pressure before retightening things up and rejigging things before taking it back up. So it's best to start early in the day and to follow the plan so that you can stay safe. Here is one example. Oh, sorry, you go, Brett, if you have another question.
There's other questions, but I mean, yeah, that was a pretty fantastic answer on that. That's interesting. So when you say that, like, you can't use a check valve, so even if you're pressure testing the section below, a check valve is not sufficient enough above to be able to provide that level of pressure containment that you need. You absolutely need to create that sectioning done with block valves.
Double block and bleed valves, yeah. It's required to keep people safe. A check valve can help as long as they're put the right way. However, double block and bleed is always recommended.
So that kind of leads into one of the questions here. So, you know, how do you decide how to, you know, break up a large pipeline into specific test sections? What kind of logic do you have to go through and analysis to make that plan?
Louise, I'll let you take that one because you design more pipelines than I have in my life.
For sure. So the two main considerations there are your volume of test medium that you are going to have to deal with. So if you have too large of a volume, you'll probably want to break it up into multiple test sections. And the second consideration is really around your elevation profile, because if your elevation profile or your elevation difference is too large, you will need to consider or explore the possibility of breaking up into two test sections or multiple test sections so that that differential is reduced.
Yeah, and then another comment on that, sometimes it's also based when you have a really flat line, you think, oh, let's just do the whole thing because there's not too much elevation. But you also want to make sure that the relative amount, if there is a leak, that you'll be able to detect it on your leak test portion of the test. So you have to watch that proportion. And that's why you should really work with your engineering service provider, such as a competent individual like Louise, to define that for you.
Oh, that's great. Thanks for that insight. So, you know, a bit of curiosity here related to, like, you mentioned in your presentation, of course, when you're doing a pressure test, you've got these two different pressures you put it at. You got your strength test and your leak test. You know, the strength test, you know, why not leave that on for the full 8 hours? What is the purpose of having the two separate tests, and why do you want to depressurize after 4?
So it's my personal preference. So you don't actually have to pressurize, but there is in my opinion, it's the best case scenario to take a little bit of a deep pressure. And what it does is it reduces the amount of stress seen on the line, as well as it gives you a chance that if you were seeing that gradual falling of pressure throughout the test, that when you bleed it, if there's any entrained air, or you can get the test section to actually stabilize a bit quicker during your leak test section. But it's a operator dependent component. You just need to make sure it's 4 and 4, and you just classify one separate than the other.
Okay,
Yeah,
well, it's pretty common practice, those. Sorry, Louise.
Sorry, I'll just jump in. One other thing to consider is that depending on the stress level during your strength test, you may actually be required to reduce that in order for somebody to perform an upfront visual inspection in a safe way. So there are limits in CSA Z662 and many operator guides that limit the maximum stress level during the leak test visual inspection.
Okay, no, that's good insight. And this is pretty commonly done with most operators, or just in a few case scenarios?
I would say most of the tests that I've been involved in, there's been a desire to reduce the pressure down just to provide that extra level of safety during the leak test visual inspection.
Awesome. Thanks for the insight. Well, it kind of leads into a little bit of the next question on here. So, obviously when you're pressuring up the pipe, you're trying to look for having your pipeline fail on that. But, what is the possibility of this action causing strain or potential damage to the pipe, even if there's no failure that actually occurs during the test?
Oh, that's an advanced question. You can take it if you want, Louise.
Sure. So there's 3 ways I would say that we would avoid detrimental strains. So the first one is for sure understanding the elevation profile, understanding your critical points, and setting your maximum pressure in a way to keep the test in the elastic region if you can. If you are testing at or above the SMYS, then pressure volume plotting will be crucial to avoiding excessive strains. And the last one is a prudent fill rate. Particularly if you're doing projects with, say, HDPE or other non-metallic materials. There's guidance in the code on different stages of kind of pausing the fill and letting it strain out before continuing on with the pressure test, but also just a prudent fill rate will avoid just any excessive localized strains as it slowly starts to expand due to pressure.
Awesome. No, thanks for that comments on that. Moving on, would you guys ever consider using pneumatic testing on a pipeline, and maybe provide a bit of context of what that is and when you might want to use that?
So I'll go first, and then I'll hand it off to you, Louise. But pneumatic testing is not a good idea for mainline or even gathering pipelines due to the amount of stored energy that you get when you're actually trying to achieve pressures such as 9930. It's like creating a bomb. And so for that reason, due to the safety concerns in it, it is not an allowed test medium, and wasn't even covered in this webinar at all. But I don't know, Louise, if you have more to add to that.
Yeah, that's essentially it. I mean, it's important to stress just how dangerous, how much energy can be stored in a piping segment at high pressures and at large volumes. And another consideration is just all of the additional approvals required. If your pipeline is crossing a road or other considerations, or other areas where you might need approvals, those can be significantly more challenging if you're proposing a pneumatic test. So a pneumatic test is really a last resort, and you have to be able to defend why you cannot use liquid. It cannot be done just out of preference or out of convenience, typically.
Okay, no, fair enough. Certainly our chat was pretty lively on that topic on there. So thanks for that clarification. I want to talk about the process there mentioned about dewatering. So in your presentation, Nicki, you mentioned that we, will typically wash the pipe with a methanol water wash and then apply a corrosion inhibitor after. I guess I'm curious, what's the justification for wanting to use specifically methanol water? Are there any environmental concerns later on with trying to get that water out? Like how do we dispose of that product afterwards on it? Yeah, can you talk about that?
Yeah, sure. So we went around in a bit of a circle about, when do you want to apply a water methanol wash? Do you want to apply a wash? In our experience, which is mainly a liquid operator, it's just good. It's a quick practice to help speed up activities, and it just is there to pick up residual water. The way that it's applied, I'm definitely not a pigging expert, but I do know that they catch it with a pressure truck on the other end and they dispose of it. So, Luis, do you want to add anything more to that?
Sure. So definitely from an environmental perspective, it is something that needs to be taken away and disposed of properly. It can't be returned to the environment. The benefits of the methanol are really that it basically, as Nicki mentioned, it absorbs some of the liquid water. Whatever is left within the pipeline is basically improves the evaporation of freestanding water. And the other benefit is that it reduces the freeze point of any remaining liquid. So that can be beneficial to, say, gas systems.
Well, that's a very excellent point on there. No, thanks for that. Moving on to another question on here. So, I think for the most part, we've talked about having, pressure testing in general on that. A lot of people consider it mostly for new pipelines, but, in the case, for instance, if you've got, class location has influenced what you're allowed to run your MOP along your pipeline, and you want to have a new pressure test on there or rehydro test to prove that your MOP is safe within that, and say you've got a 50-year pipeline, for example, what are some of the complications and considerations that an engineer has to take into account before executing that?
Yeah, so that's another super complex topic, not really fundamental. Short answer, consult your integrity representative at your company. There's a lot of integrity work that would need to be done to even get ready to pressure test. Just to kind of list off some of them, you're likely going to need to, especially for a 50-year pipeline, likely do an axial crack inspection to make sure you understand your lack of fusions and any possible laminations in your material. Also would recommend doing a magnetic MFL tool run to understand your metal loss considerations, internal and external, and burst pressure considerations, all prior to even starting to undertake putting a test through. Considerations need to be made at what your maximum pressure is going to be for that test. So there's different types of burst failure calculations that can happen, and there needs to be that balance between, should we go to all this effort or should we just reroute the pipe around whatever is causing that issue. And then on top of it, there needs to be a bunch of considerations for environmental potential failure. When you're retesting pipe, particularly old historic pipe, there is the potential of, tools are tools and they have great sensitivity and detection rates, but it isn't 100% of the time. And so how you pick those test sections so that you can isolate it and locate where that failure may be needs to be a part of that test plan. So what I presented today is mainly for new pipeline construction, and what's in that test plan for repurposing pipe needs to have a whole bunch more integrity assessments to it and a whole bunch more contingency planning than typically expected. I saw in the chat there was a question about how often do pressure tests fail and repairs required. I would say in the last 10 years, I know of 4 or 5 tests that have failed, big mainline tests. They're all associated with real close long seam failures near the girth weld. I'm not sure, I'm not going to talk about the steel mills because I don't work at a steel mill, but what happens when they do pressure test it at the steel mills, they have these huge, massive platens that come together and they squeeze on the end of the pipe. And when they squeeze at the end of the pipe, what they're doing is actually reducing the amount of hoop stress that's seen near the girth weld of where the weld is. And so that's typically where, mill QC doesn't pick up those potential lack of fusions. And so during the test, it actually pulls it apart and you'll get a failure. So they do happen, and repairs are simple. In the case of steel pipe, you just go in there and you cut it out. And then you need to redo a test to make sure that there wasn't another leak that you didn't know about. And in a test failure, I think James asked another question about, what records do you need to keep? You need to keep all the records that you did if you had a successful test. Plus, I would recommend you to go check out CSA, as there's a list of requirements that you need to do in the event of a failure as part of your investigation. And I'm sure the AER has additional requirements that you also need to submit in the event of a failure. So.
Well, perfect. I think you just rattled off my next couple of questions here. So we've had a huge, very active Q&A and questions all throughout the chat on here. We are running pretty much at time on here. So I'm going to ask just simply one more here. So thank you everybody for all of the great questions you submitted. I apologize if we didn't get to your question on here, but I'm curious, how exactly, so you have a pressure test and then you have a failure, right? How do you find out where that failure happened? What can you test? What if it's a very small failure where you only see like a small leak? Do you think you'll even detect that? Do you know where you would be able to find it?
Yeah, so if you do a proper leak test where you get it to quote unquote lock in, which means that pressure and temperature are stabilized and you're not getting that delta, you will not, and again, if you design your test sections right, you will not have that slip through the cracks. Now, if you can't get it to stabilize, now you need to think about, well, is it not stabilization, or do I actually have a leak? In that case, I would recommend that, again, you contact your integrity professional at your company and start lining up potential inline tool inspections to either identify the crack, or you can go with some other technology, which is like a sniff test, odorant test, where you can find where the leak is coming from in order to locate it. And so I learned my lesson last time I gave an IPC presentation on pressure testing. A lot of people have extra questions. Luis Azucenza has a bunch of experience, and I highly recommend reaching out to him, and he can help set up a pressure test specification at your company, or modify the one that you have, or even help you with your next pipeline project. So I have a lot of gratitude for all the work that the last decade plus of us together. So thanks again, Louise.
Oh, thank you.
No, that's perfect. Sorry, go ahead, Louise.
No, just again, thanks to you and Nicki and to everyone today. Very great Q&A session and presentation.
Absolutely.
I hope your inbox is flooded.
No, I couldn't have said that any better. Thank you both so much for joining us today. Nicki, fantastic presentation. Really appreciate everything that you presented. And Louise, really appreciated everything that you contributed to this. I know you helped a lot with the technical content behind it, and you provided some fantastic answers during the Q&A. So really appreciated having you both on here. I think this is an excellent presentation. Like I said, a record attendance for one of our sessions, so that's fantastic. And to all the audience as well, thanks for your contributions and joining us today, and contributions of all your great questions on here. So with that, what I'm going to do here, I am going to close out here. Thanks everybody for joining us. We do have a couple of new webinars upcoming in the near term here. Be sure to follow us on LinkedIn if you haven't already, just keep up to date with all the latest updates. So thanks again, everybody. Happy Friday and have a great weekend, and we'll see you next time.
Awesome. Happy New Year. Thanks, Brett. Take care, everybody. Pressure test safe.